Hi everyone, my name is Ravish and I work at PinkApp on TiDB as a solutions engineer. And over the next 20 minutes or so, I'm going to show you how to build agent memory for your AI agents using just SQL. And there's also a demo halfway through, so hopefully you stick around and let's get started. Okay, so before we get into TiDB real quick, I want to talk about why agents are different. And it's because they hit a database in completely different ways than the apps you worked on before. And there are three big things. First, agent workloads are bursty, right? So one agent might be running out flat for 10 seconds, and then the other one might be sitting idle for 2 hours doing nothing. And your database has to handle both without costing you a lot of money. Second is you're dealing with massive concurrency. It's not an app with 1,000 users, but instead you're running millions of agents at the same time and each with their own state. And third is constant context recall. So basically, every step the agent takes, it has to remember what just happened. Otherwise, the whole thing will fall apart. And those are the three things you can't really skip. So let me quickly show you what most teams end up doing today. So here's the situation. Let's say an agent finishes a chat with a user. Now the user comes back tomorrow and the agent has no clue who the user is. It's like the conversation never happened. So to fix that, what most teams end up doing is they run three different databases plus a bunch of ETL pipelines, and that's their memory layer. So you've got your regular database for storing chat history, user accounts, that kind of stuff. And that's the source of truth. Then, on top of that, you have a vector database for semantic search, so you can store embeddings of whatever the user said. And on top of that, you have a search engine because vectors are bad at exact matches. So if the user said a word like, let's say Tokyo, you want a keyword index to actually find that word Tokyo. And then there's the fourth piece nobody really talks about, which is the glue layer. That's your ETL jobs, your message buses, the cron jobs, something to keep all three of these things in sync. And your team has to write and maintain that code. So now you got three databases to run, three separate bills from three databases, and three things that can break. And on top of that, your data is never really in sync. So it's just a lot. Now, look, if you are building just a regular application, you can kind of sort of live with this. It's annoying, but I guess you can deal with it. But however, with agents, though, this stack breaks in a bunch of ways, and here's why. So the first one is stale data. Your vector index is always a few seconds behind your main database, so the agent ends up reading old data and old facts. So let's say user updated their address an hour ago, but the agent is still using the old one. Then you've got the read after write problem. So say your agent just placed an order and 2 seconds later, the user asks, what is the status of my order? And the agent says, I don't see any orders, but the write just happened, but the read side hasn't caught up yet. And then the third one is partial writes. So agent, let's say, does a multi-step thing, like processing a refund, it deducts the balance, logs the refund event, triggers some sort of an email. Now, midway through, the email service dies. So the balance shows that the refund was applied. The log says that it happened, but the user never got the email. Then the user calls the support and support sees the logs and says it looks fine. So you're stuck explaining a ghost refund. And the last one is a connection fan out. So for example, let's say you have 10,000 agents times the three systems is basically 30,000 connections you need to maintain and manage. And your connection pools can, basically keep up with those connections. So your latency goes up when the traffic spikes and you spend half of your time managing connections instead of building features. And look, this is all like not just theory or hypothetical. This stuff actually happens in production, and you only run into it once you're at scale, which is the worst possible time for it to happen. And that's where TiDB comes into place. So real quick, in case you haven't heard of TiDB before, here's like a quick summary. So first, it is a distributed SQL database, so it can scale horizontally across nodes. So no sharding, no rewrites, you just add nodes and capacity whenever you need it. Second, it is MySQL compatible. So any drivers you have, any ORM, any tools you're using with MySQL, it works with TiDB as well. Third is it has an HTAP and an AI engine. So transactions, analytics, vector search, and full text search all live in the same database. And fourth, it's used in production by many of our customers like Manus, Pinterest, Diffie, and a lot of others. And that's basically a quick overview of what TiDB is. Now let's go ahead and get into the capabilities. All right, so here's what TiDB gives your agents. So the first three rows fixes the three data problems that we just talked about. And the last two are extras that kind of just makes your life easier when you're building agents. So the first one is agent state and chat history. That's just normal SQL. Next up, we have semantic recall, which is a vector column with an HNSW index. Next is keyword search, which is a full text index with a multilingual parser. So it can handle English, Spanish, Japanese, whatever you throw at it. Then we have embeddings on insert, which is nice. So there's actually a SQL function called embed_text, which basically you can give it some text and it will call the embedding model and it will store the vector for you in the table. And the last one is hybrid retrieval. So you can run a vector search, and on top of that, you can run a keyword search, and then you can combine them with some sort of ranking algorithm. And we're going to see all of this during the demo in just a second. Now, just one more slide, and then we'll get into the demo. So this goes back to what I said at the start about agents having different needs from a database. So the first thing you get from TiDB is you get scale to 0. So if you have idle agents, they literally don't cost you anything. You're only paying for the request you actually run. So when your traffic is bursty, your bill is bursty too. Then you get database branching. So you can spin up an isolated database per agent in just a few milliseconds. So every agent gets its own workspace, totally separated from everyone else. Third is resource control. So you can cap how much each workload uses. So if one agent goes off the rail, it doesn't take down everything else. And the last one is fast scale out. Compute and storage are separated in TiDB, so when the traffic spikes, the database can add capacity in seconds instead of minutes. And okay, that's enough slides. Let me show you in the database. Okay, so in demo 1, we're going to create the memory table. Okay, so here we are in the SQL editor on a free TiDB cluster, and I'm going to run the whole demo on just one table. So up top, you see normal columns like a user ID, just a regular ID, content, a timestamp. The interesting one, however, is the embedding column. It's a vector with 1,536 dimensions, and it is a generated column. So every time a row gets inserted, TiDB calls the function called embed_text, which is pointed at my Azure OpenAI deployment, and it generates the embedding and stores it. No Python, no pipeline. Plus, at the end, you also see there's a vector index for semantic search and a full text index for keyword search, both on the same table. And as you can see, the table is created. The step number 2 for the demo is inserting memories and seeing the data. So now I'm going to drop the 5 memories for user ID 42. So as you can see, they are plain English strings, no embedding code in my script anywhere. But TiDB is calling the Azure OpenAI in the background to generate the embeddings. And there they are. So you see 5 rows for jazz, vinyl, peanut allergy, Tokyo flight, email preference. And yeah, that's our data set that we're going to use for the rest of the demo. Step number 3 is going to be semantic search. So here the agent is asking, let's say, what does the user like to listen to? So notice my question doesn't share a single keyword with anything in the database. There's no listen, no like to, just jazz and Miles Davis. But as you can see, the jazz row comes back first, and you can see the distance is 0.49. That's the closest match by meaning. So TiDB took my English question, embedded it, and ranked rows by similarity all in one SQL call. Step number 4 is keyword search. Now, sometimes you want exact word matching instead, so vectors are kind of bad at that. So here we're using a full text search to check if the user mentioned a city. And once we execute the query, you can see there will be a row, the Tokyo row, which is the exact match. And then you can also see the score of 1.34. And the big thing here is this is the same table I just did vector search on, no separate engine to keep everything in sync. Step number 5 is hybrid search. So, okay, I guess this one really matters. So real hybrid search isn't just one query. It basically is 2 searches plus a ranking step on top. So what's happening here is the first common table expression is running a vector search, grabbing the top 10 rows by meaning. And the second common table expression is running a keyword search, grabbing the top 10 by exact word match. Then we're combining them using something called reciprocal rank fusion, or RRF. And the data is super simple. Rows that rank high in both lists basically wins. So I'm asking what dietary restrictions the user has. The vector is looking for the meaning. Keyword is looking for the word like allergy and peanut. And as you can see, the peanut allergy row comes first because it scored well in both of these searches, the vector and the keyword search. So one query, one database, no separate engines to keep everything in sync. And the last one is going to be ACID transactions across tables. So real agents, as we know, do multi-step writes that have to land together. And there are 2 tables here. So there's a memory table you've been seeing, and there's also a separate user facts table where we track aggregate stats per user, like their trips and their memory count. Now, what's happening here is I'm wrapping a transaction around 2 writes, insert into memories, update the user facts table, and then commit. And as you can see, the new memory is in the memories, and trip counters went from 0 to 1, and memory counter went from 0 to 1 as well. Both writes landed together, and if either one had failed, neither would have stuck. And that's real distributed ACID across multiple tables. Okay, so that was the whole demo. Now let me close out with a few companies actually running TiDB in production. And these are real numbers and not just benchmarks. So the first one is Manus. They are an AI startup company, and every agent gets its own database spun up in milliseconds. So over 1.5 million of these agents right now, and they moved over to TiDB and got to production in 2 weeks. Then we have Diffie. They are an AI dev platform company, and their actually backend used to be 500,000 containers, and they moved all of it onto TiDB. So now they just have one engine that does everything. And then we also have Pinterest. I mean, they are not an AI company, but the problem they had was very similar. They had 6 different databases systems doing different jobs. Now they'll have only one, which is TiDB, and TiDB is doing basically 1.3 million queries per second for Pinterest. And across all three, the story is basically the same. You have less stuff, more speed, engineers building product instead of patching pipelines. So just a quick recap before I wrap up. With TiDB, you get auto embeddings on inserts, no more Python pipelines. You get vector, full text search, and SQL all on the same table. So you've got one source of truth. You also get hybrid search the right way, 2 searches with RRF on top. And the whole engine is built for how actually agents run with branching, scale to 0, and resource control. And the best part is you can spin up a free cluster in 30 seconds and it can scale to millions of agents. All right, so if you want to try this, here's where to go. So you go to tidbcloud.com, which is the main one. So you can spin up a free TiDB starter cluster, no credit card, and your cluster is going to be ready within 30 seconds. TiDB also has a native Azure OpenAI integration, so you can very easily integrate your Azure deployment. For agent patterns and the customer stories I just talked about, you can go to pingcat.com/AI/agentic AI. Now, if you are a Python developer, we have a Python SDK, which you can install by doing pip install pytidb, and that gets you hybrid search and RRF in 3 lines. And for Cursor and Cloud users, we do have an MCP server and a bunch of agent rules on github.com/pingcat/agent rules, so you can drop TiDB directly into your AI coding workflow. And that's pretty much all I have. So thank you all so much for watching, and go build something cool with TiDB and stop running 3 databases when you only need one.